wait a little bit. Meanwhile, I mean, you share the screen and then you can start. Excuse me, because can you make it full screen? Can you make it full screen, please? Well, with on the presentation mode, maybe. Okay, okay, thank you. Yes, yes, yes.
Aquí está. Aquí está. Pone el... Sí. No, déjalo. ¿A mí? Sí, está.
Vas a mandarlo.
Hay que ver. Pues ahí no quieres irte a otro lado.
And of course, you can write it in a differential form. This equation,
Este aquí.
one minus sigma v by actually kind of subtracting v plus 1 minus ut, which is actually du. And this 1 minus this minus u, so that will be a quadratic equation.
¿Se escucha muy feo?
Right. And then near the critical point,
Se escuchó que se escucha bajito y empezó ahorita. Muy feo.
Fixed point, you can expand it to small, then essentially you get this, and it does this, and then and so now
Puedes escribirle que tienes problemas técnicos.
And that gives beta plus gamma is 3 by 2, and the equality is minus alpha is linear. And that says that it is linear, so we get beta already got half, then gamma half, and so beta plus gamma is 3 by t, and then that means d nu is equal to this, and then the effective critical dimension is 6. And the correlation is 4, that you got, and these are the things, and many other things in that also. Now, these things also says that when you can get a critical peak, then there will be avalanche. I mean, I put something, and there will be fibers. I mean, now,
Si gustas es mandarlo desde aquí.
extra load on the system. Then up to a point when the next fiber fails, and then I stop. Then there will be some failure that at least the next one has failed, and then that extra load shared by all of the survivors. That made cascading other failures. And then again, so they use some and it stops. Then that leaves an avalanche size. And you can calculate, you can get avalanche distribution, and that's one important avalanche distribution for the thing. And it is there but as I mentioned,
Para ese apaño me pones permiso.
uniformly, now it's uniform, but with this sigma, which is until the next plane, uniform sigma is sigma. Then it will be replied by 2, and that was replied by.
Es que no va a haber tiempo, se no hay tiempo para resolver.
Sorry, because we have 5 minutes left,
Okay.
including questions. So if you can.
Okay. So this is the thing, and then let me go very quickly. That these avalanches are of different sizes, and from there we go to. These are things that it is like you can consider this as if a community has got income distribution or wealth distribution, and statistics from many indexes. 1914 in economics, and it was from Lorentz curve. I mean, the Lorentz curve is, avalanches. I mean, like, avalanches, the size of avalanches, and the cumulative size of the fraction of the avalanches are in the y-axis, and the number, I mean, cumulative fraction of avalanches on this side, and it's ordered.
No.
Where you measure the avalanche inequalities, and then it is going to beyond 0.6% stop it, because very soon it will fade. So that's the kind of precursor study which has been, and many more. These are the references so that they are. Now I have stopped. I will stop and perhaps go for questions.
Thank you. Any questions? No. Well, it seems that we don't have any question. Actually, well, we are a little bit late, just on time for the next talk. So we thank you again, and thank you very much. Thank you.
So,
So,
thank you. And Mario, I mean, I missed your talk.
Okay, so we are going to put the next talk. I, so, okay, so if Matteo can appear on the screen and put, hi, Matteo, and share your screen, please.
Yes. This one. Okay, can you see my screen?
Yes.
Okay, very good.
Okay, so yeah, so next talk is by Matteo Marsili from in Trieste. He's going to talk about price formation, market impact, and information thermodynamics in simple models of financial markets. So please go ahead. Thank you.
Okay, thank you very much.
Yes, we can see them here.
Okay, so actually,
Do not change much, so the plasticity is rather suppressed. Whereas in deep layer, the plasticity is still very high, and this is actually what you expect, because if the internal representation with depth approaches an abstract representation which is invariant and is independent of the data, then the information on the data should necessarily be in the weights. So if you change the data set, the weights should change a lot. Whereas if for shallow layers instead, in shallow layers, the weights do not change much, which is essentially in line what the capacity of these networks to represent even data set with which they have not been trained. And this is what is called transfer learning. Maybe some of you have heard about it, but transfer learning means that you can train one of these networks for supervised learning on one data set, and then this network performs reasonably well also on another data set if you just retrain the output layer, okay, without the need to retrain on all the layers, okay? And by the way, this dependence of plasticity with depth is the same thing that happens in your visual system, because you know the retina is essentially hardwired at birth. So the connections of neurons in the retina is fixed at birth. In the primary visual cortex, the plasticity is essentially suppressed after a few months of after birth. So essentially, this trend is essentially the same of what you see in say in the brain. Okay, so this is my summary. So what I wanted to tell you is essentially a picture of what happens in as you process more and more information we use this deep belief network, but the picture I think should be rather general. You go from a very generic representation to a very abstract representation. This generic representation is, in this case, a pairwise Ising model. And the abstract representation is this maximum relevance model, which is the hierarchical Fisher model. Now, the shallow layers are described by a very complex model, whereas the model, this abstract model is a very simple model. I mean, in complexity in terms of information theory, in terms of, stochastic complexity of models, okay? And then, to a large extent, the shallow layers are hardwired, so in the sense that their weights are very generic and reproduce low-order features, whereas in deep layers you have more plasticity. The layers are more flexible, and essentially you store the information much in the same way as you do in Hopfield-like models. Okay, so I think I thank you very much. By the way, I don't see any of you. I only see my screen. So, but thank you very much. These are some references if you are interested in any of this.
Thank you. Maybe we could try to show the audience with the camera. Yeah.
Okay. No, but yes.
Okay. Any questions?
Okay, Matteo, just a kind of trivial question. I mean, you are showing kind of layers, up to 16 or 15 layers. And these WIJs are actually to be, how do you, you are indicating too many values of WIJs. These interlayer interactions between the, whatever, neurons or something. And 16 layers, how does it, does it not overdetermine everything? And isn't there a problem? How many real WIJs are in between any two layers? How many WIJs?
Okay, so this is the architecture that we use. So these are very over-parameterized models. So these are models which have many parameters. So, for example, the first layer has 500 nodes. The second layer is 250 nodes, which means that the parameter
you are decreasing. Okay.
Is essentially 10 to the 5, already between the first and the second layer.
But first and second will have 500 into 250 layers. 250 WIJs.
Yeah, 10 to the 5 parameters, essentially.
Oh, okay. You are actually.
They are very over-parameterized, and this is true for all these machine learning things. Even say now, this ChatGPT has billions, tens of billions of parameters, and so I mean, this is all this machine learning business is very, very different from standard statistics where you talk about overfitting and all these things. I mean, there is no overfitting. I mean, for reasons that are partially understood, but I don't know if you want me to go into this, but yeah. But they are very over-parameterized.
Yeah, okay.
Okay. Any further question? Any other question? Well, I had a question. The biologists or psychologists sometimes define learning as changes of behavior due to experience, and meaning that it's kind of a dynamical process in a way. And how is that this fit in your description of learning? Is this
Probando, probando. 1, 2, 1, 2. Probando, probando.
Probando, probando. 1, 2, 1, 2. Prueba de audio. Sí, probando. Ey, 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 ey. Prueba de audio.
¿Empezamos?
Okay, so I'm very happy to welcome you to the second half of the morning session and welcome Alejandro Hernández, who will talk to us about a preliminary data analysis of the individual income distribution in Mexico. Thank you.
Thank you very much. I'm very happy to be here in this institution, CUCEI, physical. And I want to thank to the organizers for the invitation. I appreciate it a lot. And I'm going to talk about some data analysis that we made on Mexican income data. By the way, I include to my partner Héctor Coronel Bricio because he performed the fits. But first of this, and since the talks on this meeting had been very high level, I would like to speak a bit about this fundamental problem before the results. The results are very preliminary, so the econophysics, is the application of methodologies created to study physical systems applied to economics. And then we are going to present some remarks about the empirical universal properties of financial data, in particular markets data, and for this reason also income data. And I think this will be interesting, and there are some points that they impressed me very much about these problems. We have some work on income data and wealth distribution problem, and you can see all the publications of our group in my personal homepage. But in the topic of the wealth distribution, we have one simulation using this ICSP model, and we reproduce this kind of income distribution. We have some, we reproduce also the wealth distribution using this punctuated equilibrium for these chain models, and we reproduce these properties of the income distribution, and we reproduce the universal properties of the income distribution using the game of life and so on. This is very interesting because these properties appear. Okay, in economics, they say the income distribution is made from the combination of two distributions. One Gibbs or exponential, or some people say it is a gamma for the low, medium and low region of income, and a power law for the richest region of income. And this property is okay. In economics, they mention this still is a fact, but it appears in different societies, in different countries, in all times. And for this reason, in economics, they say it's universal, but appears also in different physical systems. And I want to show some of them. Okay, in econophysics, some current research areas, okay, sorry. Okay, it's here. The classic is study the time series of financial time series like stocks, currencies, financial indices, size of firms, wealth distribution, GDP, network analysis of economic phenomena, stock market crashes is a very interesting topic, and more recently, agent Bayesian models to reproduce, to construct markets, artificial markets, and study them, distributional properties of stock markets, let's say facts, volatility, correlations, etc. Automatic trading systems. Also, some people that is interested in automatic trading systems, random matrix theory, and economic complexity, and so on. Then maybe, okay, a complex system is a system formed by a very huge amount of components or agents, and there are interactions between them. This is very important, non-trivial interactions, and there's some properties that emerge of this system that they are not easy to forecast. And there is some auto-organization of the system and so on, and financial markets and the society are complex systems. For example, in finance, there are a lot of traders that are buying and selling stocks or titles or futures contracts or options or whatever, and they observe what is going on in the society, the governments. If some government has a lot of debit, if there are some war in some place, you see all this. Also the big companies, the big banks, all these agents, normal people also, normal people, small investors, people that is getting some pension of the government, all these agents interact, and the traders observe this information, and they determine the price and the evolution of the price in financial markets, and also in the case of the society, when people exchange money or invest, they increase their wealth, and this is also a complex system. Okay. Okay, I spoke about this. This is some plot of the Dow Jones, this index of the American market and stock market, and you can see how the price changed on time, and this price is, you can see like the pressure of one system, because there are lots of traders, many traders, and participants of the market that they think about the price. They buy the stocks that compose this index, and they interact with the information and the state of the market. Okay, a micro state of the market is all these lists of traders, the book of orders, where the people is trying to sell or trying to buy the stocks that belong to the Dow Jones index. And that is a micro state of the market when the price, when there's some order that executes, some buyer buys the stock, the price formed, and in every second the price, okay, not exactly every second, every time there is an operation of the market, the price is recorded, and then you can see the evolution of the price. That is a micro state of the market, or in this case, for the Dow Jones. And we don't work directly with the prices, we work with log returns, or people mention them as variations in general, or log returns, or only returns. Sometimes people work without the log. And then these returns or prices, they have very important properties, empirical properties that for every market, for every stock, appear universally. And you know that returns, okay, sorry. Everybody that knows that returns decay as a power law. There is no correlations for returns, or the correlations are very short in time, maybe a few minutes, and then the autocorrelation function decays to zero. There is a symmetry gain loss. It's supposed it's easier to construct, to destroy wellness that construct it. The aggregation allogenity, when you take the scale of time bigger and bigger and bigger for the returns, the distribution of these returns converge to a Gaussian. There are clusters in the returns and volatility. If you plot the returns on time, you see that big events appears not alone, not isolated. The big events appears in clusters, like when you see one seismograph, that seismograph is detected some earthquake. There are some vibrations that correspond to this earthquake, and they don't come alone. And etc. So this is observed, or these empirical properties, they are not only natural in financial markets. You can see this kind of properties in meteorological time series. You can see also these properties, or these statistical properties in traffic and transportation data, in biological and epidemiological data, and in social media, and in many systems, you can see the same properties. So they are shown in different systems, not only in the market, but in the market economics, they call them stellar facts, and in some sense, they are natural. You expect to see this kind of properties in different complex systems, and nobody worried about this. Then I would like to show you a paper that we wrote some years ago that, in my opinion, is very nice, but maybe you would think this interesting. And the fact is, in the paper, we work with the game of life. Game of life is a cellular automata invented by John Conway. John Conway is a very famous mathematician. And, okay, what's going on? Okay, maybe I can show you the paper directly. What's going on? The idea is you have this cellular automata is a complex system. Maybe before this, okay, here. Let's see the rules of the cellular automata. You imagine a lattice formed by cells. Every cell can be in two states, or 0 or 1, or we call them also dead or live or black or white, whatever. And this system evolves following these rules. You have a cell like this, central cell, and you have a neighborhood. In our case, the neighborhood that is interest is this. Okay, 9 cells around the central cell, and a dead cell means the central cell of the neighborhood will reborn at time t+1 if in its neighborhood there are exactly 3 alive cells at time t. The second rule is a living cell will survive at time until time t+1 if in its neighborhood at time t there are 2 or 3 alive cells, and finally a living cell will die at time t+1 in any other case. And then you can imagine this lattice of the game of life. The cells are changing, black and white, they're changing the colors and evolving to some new configuration. And what we did was to plot a coordinate system in the middle of the lattice and follow the evolution of the center of mass. The center of mass you calculated. Imagine, okay, assigning 1 unit of mass to every alive cell and 0 mass to every dead cell, and then you get the evolution of this every microstate and the evolution of the macrostate that is the center of mass moving around the coordinate axis. In 2 dimensions, you have some nice random walk like this, not exactly random walk, but you have something like this. And to make the problem easier, you consider only the distance to the origin of the center of mass, and you have something like this. You have this random walk. That is, you have the returns like in the stock market or different systems. You have these clusters, clustering volatility. You have the distribution of returns. That is very nice. You have power laws of these distributions. Okay, power law, exactly like in the stock market or in different systems. You have the aggregational Gaussianity. When you increase the scale of these returns, the returns distribution converges to a Gaussian. You can see the Gaussian in the middle. You have the autocorrelation function decaying to 0. The absolute value of the autocorrelation function decaying as a power law. And you have all the different stock market properties or empirical properties or stylized facts. That thing is very nice, I think. Okay, for which reason I spoke about this? Now I'm going to pass to the problem of wealth distribution. The problem of wealth distribution, there are many explanations for the poverty and inequality in the society, and some of them are very, very popular or very, very, well considered. For example, sometimes the exploitation of man by man caused that 50% of the countries were communist at some point, trying to supposedly trying to avoid this inequality or poverty of the society. Different religion ethics, lack of qualified force, dependence on external technology of a country, low levels of internal savings, non-equilibrium between exports and imports, low cognitive and schooling skills for population. This is very important because there are studies that spoke about this. They are not speaking about low level of education. They spoke about low cognitive and schooling skills, level of corruption and quality of democracy, and finally the explanation given by Piketty, capital rate of returns exceeding rate of output and income, and many more like. There are many more. And I would like to mention here that in different parts, speaking about inequality or poverty, and inequality and poverty is totally different, but some social scientists, they don't make any difference between poverty and inequality. That is very different. These concepts are very different, but in some point, in some studies, they speak about inequality and poverty changing the terms without any difference. And the bibliography cited about the causes of the inequality and poverty, you can see here, there are a lot of information about these topics. And what kind of stylized facts are the stylized fact that the distribution of wellness, distribution of wealth display? The distribution of wealth displays one behavior like this. Gibbs or log normal. Physicists say that is a Gibbs or a gamma, and economists say that is a log normal. This is the distribution of income for the low medium sectors of population of income, and a power law for the high sector of income in society. So the richer sector of the population, they have a income distribution following of the Keynes-Pareto law, and the poor and medium class region, they have an income distribution decaying as a Gibbs or log normal or gamma. When I spoke about income, in some papers or some studies, they don't discriminate between income and wealth, but you know that income is very easy to measure. In some countries, you go to the taxes office and you can get the data about how much every people gain every year, but in Mexico it's not easy. But in general, that the studies are made on income and not in wealth, because nobody is going to say how many gold lingots have hidden under the bed or whatever. And the wealth distribution has these properties. The wealth distribution is the combination of a Gibbs or gamma or log normal, depending, and a Pareto distribution. It's a combination of two distributions, and you can observe this kind of behavior, statistical behavior, in every social data of income, taxes, or pools, whatever. And this is an universal property of income distribution. Now, let me show you these plots. They are plots published in papers from Daculesco-Yakovenko in 2003, 2001, and SOMA, where they analyzed the income data for United States in 1997, UK in 1996, and Japan in 1998. And you can see that there is a Boltzmann-Gibbs exponential part and the Pareto distribution. The Boltzmann-Gibbs for the medium and low sectors of income in the population, and the Pareto for the high income sector of the population. And this distribution is the same for these three countries for these 3 years. And this is even more interesting. This paper, this is the bibliography for the three plots I showed before, and this is a plot showing the income distribution for different years, going from 1983 to 2001. And you can see that in the 90s, you have the same distribution for the income, for the medium and low sectors of income, and for the richest, this is the power low. And in the 90s, this is 90s also, and 2000 someplace here. And the distribution only changed in maybe in average, okay, but it conserves the shape, the combination of one exponential and a power law, okay? And then this stylized fact appears in a lot of systems. First was observed in the plasma distribution, okay, in plasma systems. Let's see, observed plasma physics and astrophysics. This Asagawa, Mima, and Dongband, 1985, plasma distribution function in a superthermal radiation field. Also, this say Mason and Doyle in this evidence for unknown suprathermal seed population of heavy ions accelerated by interplanetary shock near in Gaulier magnetospheric superthermal particle distributions. And I thank Professor Jacobenko because I asked him about other systems where you can see this combination of exponential and power law, and he sent me this reference, and he also sent me this reference, transversal moment of adonized charged particles in PP and lead collisions. Hydrodynamic extension of a two-component model for hadron production. The title of the paper is this, and this is the transversal momentum of this adonized charged particles shows this combination of an exponential and a power law. The Dodge top 2000 pop songs ranking, and the referencing is this. And also, Professor Jacobenko sent me the references. And finally, in the IC model, metropolis simulation, we gain loss. Okay, you have this IC model when the magnetization of a spin changed. You consider this fact as if the spin were gaining a unit of money, and Congo game of life, the system I showed you, when the cells change the state, you consider the cells are gaining a unit of money, and we have this kind of, okay, we have this work in this topic. On IC spin models and statistical weld condensation generating a weld-like distribution, we generate a weld-like distribution following this process, and ongoing game of life. Thermal and superthermal income classes in a weld-like distribution generated by Conway's game of life cellular automaton. This was published in 2020 and this in 2012. But you can see here, you have the IC model. This is a temperature of the IC model below the critical temperature, at the typical temperature, and above the typical temperature. And if you count how many times every spin changes, and you plot the distribution, you got the gamma. This is a gamma, and the power law. Of course, here this example was synchronized one parameter, but in real life there are no parameters. But for the game of life, you have something like this. You have a exponential. Now the red one is the gamma. This is the log normal. The blue with intervals, and here you have the power law. And the interesting thing is that game of life says that the distribution of the low and medium sector of population, distribution of wealth or income is a gamma, not a log normal. So it's possible to reproduce these stylized facts for the wealth distribution for different systems, different systems outside of economics or social systems. And this is, in my opinion, very interesting because the Gibbs or gamma and combined with a power law, this is not a very common combination. There are not many systems following this rule, but there are some fair number of examples to show. For the analysis, we how's the time for my talk? How long remains?
5 minutes and then questions.
Okay. We download data from the INEGI, Instituto Nacional de Geografía, Estadística y Informática. They made a pool every different amount of years, every 2 years. Sometimes they skip 1 year. They took 3 years to make a new pool, or every year. There is not a consistent interval of time. But in the website of INEGI, it was possible to download wealth or income data for Mexican population, and the data was collected by polls, asking people how much they earned. Of course, this data is not very, how to say, you cannot have a lot of confidence in this data because people don't like to say how many they earned, but it's the thing we have in Mexico. And I discovered, thanks to Marcelo Castillo, this paper, he sent me this paper where they perform an analysis of the wealth distribution data in Mexico in 2017. But I haven't read the paper. I realized about this paper only yesterday. And okay, every one of these data files, they have a variable number of entries. They can have only 10,000 entries or 250,000 entries. There are not a fixed number of entries. And okay, the gamma distribution, I'm going to skip this because of the time, but we fit the 3 parameters gamma distribution, not 2 parameters. This allowed us to move around the x-axis, the distribution. And you can see these examples of fitting well distribution in Mexico using a gamma. The gamma is the point line. Data is the line, continuous line. And this is the cumulative distribution function. We use the cumulative distribution function to perform the fit. And you can see that the data fitted by gamma the fit is very good. I don't have here the more information about the wellness of fit, but the fit was okay. The model passes all these conditions. And one thing that is very interesting is that the pool made by the NEGI, they have people that at maximum they earned 2 million people, 2 million pesos every year. So the data lacks the information about the really rich people in Mexico. This is the same, sorry. This is for the individual income, an individual person's wealth. This is for, okay, let me, okay. This is for household data, for families. And the gamma is a good model for fitting this data. This is for the individuals. And okay, there are some variations, but sometimes the model was very good fitted. The data was very good fitted by the gamma, sometimes not very good, but in my opinion, the data is well fitted by a gamma distribution for the low and medium income sectors of the population. And here is the Pareto fit for the households. And sorry, I don't have here the log plots, but the data was well fitted by power law. Okay, the asymptotic part of the distribution was well fitted by a power law. And this is for the individual income distribution. For the years, let me see what years that we fit here. I put in some place. Okay, maybe. I remember it was 1998, 1984, and 2018. These plots show that wealth distribution or income distribution in Mexico preliminary can say is follows the universal distribution of wealth. There are many more data. I am not showing all data, but only for interest, we fit the exponential of the Pareto law for every sample data sample, and I plotted on time to show the evolution on time. We cannot see any law. There are some fluctuations that at least I cannot see any law here or any evolution of the power law exponent. And here you can see the Gini index. The Gini index shows that at least until 2018, the inequality in Mexico was decreasing, but also there is no apparent correlation with the power law of the distributions of wealth. Okay, thank you very much.
Thank you very much. Thank you very much for a wonderful talk. So, are there any questions? Shoham.
So the Gini index is decreasing means inequality is decreasing in here, right?
Yeah.
So now if you go to the previous slide where you are showing that now the exponent of the Pareto law also tell us that give us some idea about the inequality, that is the rich people, how their wealth is distributed. Now, if my exponent for the Pareto law is decreasing, that means the wealth of the rich people are less than previous. Now, if you please go to the previous slide. Yeah, okay. There I am confused because you are saying for a household, the exponents are decreasing, but for the individual, exponents are higher. How is it possible?
In fact, I don't see, okay, maybe you're right, it's decreasing only in this part.
Yeah, and at the same time, it's not. The other case is not.
In fact, also it's decreasing.
So your household exponents, the Pareto law exponent for the household income, that's kind of consistent with your Gini index.
In fact, they have the same behavior. You can see this decrease, increase. Also decrease, increase. Same behavior.
And how the Gini index is calculated? It's from the household income or from the individual income?
Okay, the thing is the data includes very difference of data samples, the size. Sometimes you have a data sample of 10,000 people, and you have sometimes a data sample of 2,050 people. So I still trying to understand what's going on here. But normally in households, the family, now both wife and husband work. But there are some families where only the husband work, and he earns all the budget for the family. But
so your Gini index is from family?
No, the Gini index is for all the population.
For the whole population?
That's integration, yes.
Okay.
In fact,
leave the discussion perhaps for later. Okay. There seems to be a question from the online. Could you appear?
Rafael, could you turn on your microphone, please?
Yeah, I'm sorry, I didn't put my hand on. Sorry. Are you there?
We hear you. Can you make your question?
No, I didn't have a question, sorry.
Great, okay.
I was going to say that the stock market is the most difficult system that you could face, really. So it's marvelous that you could start analyzing these things, irregularities about it. But in general, it's quite good. Thank you. Yeah.
Thank you.
I have a question. Yakovenko showed that in the highest region of income, the Pareto people, their wealth the Pareto wealth is correlated with the stock market, right? So the very rich, have their money being shrinked, swallowed, according to the stock market in the US, because they have a lot of money there. And here you have data up to 2 million pesos, per year, which is more or less $100,000, not much, So all the very rich people, well, there are rich and super rich. I think there are two power laws, One power law that will appear for the rich, and another one for the super rich, like Slim, Azcárraga, etc. And also they should contribute to the Gini index, the inequality.
Okay. It's a question? It's an observation.
You agree with me?
Yeah. In fact, the rich people, the really rich, they have they invest in the stock market. And in Mexico, the people that invest in the stock market is minority. Also in the United States, maybe some people that get a pension, they have these funds for pension and they invest in the stock market, but not in a different way, but also invest in the stock market. But that you say is interesting and it's true, yeah. I think I agree with you.
Any further questions? I would have a question or maybe a comment. It seems to me that the Gini index may not need to have a great deal to do with the super rich, since it is rather a global measure, and it may easily be susceptible to equalizing within the middle class, within the Gibbs distribution. Is that correct?
I'm not sure because, there are some countries with a very low Gini index without super rich, like in some African countries that if you see the Gini index, you could think, this is a country where the inequality is very low because the Gini index is very low, but in reality, all they are poor. And there are some countries.
That's another issue, yes, of course.
There are some countries where there are a lot, the inequality is very huge, but the medium class, they have income not low. Everybody wants to immigrate to countries like United States or countries where there are super rich, many super rich, and the Gini index is not very low, but also not very high. But for the immigrants, it's desirable to immigrate to these countries. So the Gini index is a measure of inequality that is very delicate to take.
Okay, so then we proceed to the next talk.
Thank you.
Thanks, yeah. ¿Dónde está el conferencista? Ya.
Creo que hice una introducción demasiado larga.
Tal vez. No, pero estuvo bien. So now we are going to have a talk by Horacio Tapia, who will talk to us. I'm not quite sure of the title. Feature-based analysis of financial time series. Horacio Tapia from Veracruz. Sí, claro.
Okay, can you hear me? Thank you very much for the kind introduction, Francois. Thank you very much for the organizers. I'm pleased to be here. I'm very happy to have attended this awesome conference where I've learned a lot of things. It's very funny because it's a stochastic process conference, and right now we are on a limit of a stochastic process in which Germany is playing against Spain, and I have some value of risk set in that, so it's going to be an interesting talk. Let's see what happens. So this is the title of my talk. Oh, I'm sorry. This is what I tried to avoid yesterday, and it happened. I'm going to talk about feature-based analysis. I'm Horacio Tapia McClung. I am at the Instituto de Investigaciones en Inteligencia Artificial, which is at the Universidad Veracruzana. Through the week, people have asked, where are you from? So this is a quick show of where I come from, or rather Alejandro and I. So this is where we are, and this is the optimal trajectory according to Google to get to where I live. So we're pretty far from here. The hurricane just crossed this region, and it's going apparently in this direction. So hopefully we'll be fine. But this is where I come from. This is where we are located in Veracruz, the other side of the country. That's where the Universidad Veracruzana is, at least the building where we are, Universidad Veracruzana. Veracruz is a long state, for you that don't know. It goes like this, all around the Gulf. And we have 5 campuses along the state, so it's a big place. Anyways, it's been an exciting week. I'm showing you here a recap of the things I learned, and I try to extend and have in my head because they are actually relevant to my work. So I learned about the first heating time, about the Levy-Smirnov distribution, which is also a inverse gamma distribution. So this is easy to and fast to reproduce. And then it was also fun to change the boundary for a boundary that changes in time and see how it just goes from the exact distribution that we learned during the week. So it makes me wonder, learning about this resetting and heating times, will there be a more smart way to get out of a maze than just running randomly? Maybe if I reset myself every time I hit a wall, I could be faster escaping from this maze. So, well, this is just something that came up to my mind during this week. Also, we had some discussion on the removing phases from signals from the Fourier transform. So I did an experiment to that because it's not that I didn't believe Marcus, it's just that I wanted to see it for myself and understand what I was doing. Because as I said, it's relevant to what I've been doing, and it just got me curious how it happened. So this is a sinusoidal signal. The blue one, sorry. The blue one is the original, is the sum of 2 sinusoidal signals, and the yellow one is the one we obtain once we substitute all the phases for random numbers between 0 and 2 pi. And below is the autocorrelation function for those 2 signals. So indeed, what was said in that talk happens over here, which it should, of course. This is a random signal, completely random signal. So in completely random signal, the autocorrelation function falls to 0 real quickly. So again, we remove we don't remove the phases, we substitute the phases for random numbers on the Fourier transform, and the correlation function stays, the autocorrelation function stays the same. And this signal here is actually a segment of a return time series, which is the main subject of my talk today. And again, the expected behavior happens. So with this preamble, let me get into my agenda. I'm going to quickly talk of machine learning. We already had a very nice presentation on artificial intelligence and machine learning methods, more directed into a different area, which is an interesting research area on the merge and between statistical mechanics and learning processes that are given by neural networks. I'm going to briefly talk about time series and features with reference to the machine learning ideas, a set of tools for selecting time series features that we have explored, and how they apply to the financial returns that we've been studying. So machine learning, it's just a subset of artificial intelligence, which is not the generation of robots that are going to take the world or going to finish with the jobs of people and become super. It's just a computer science research area in which we try, or actually the computer scientists try to develop and study statistical algorithms that are good on finding patterns from data. That's it. And the process of finding patterns from data in this research area is called teaching. And they teach computers, and by teaching they mean they just show the data to the algorithms. The algorithms are good into analyzing the data and fitting parameters And so they are able to learn the patterns from the data. The idea of artificial intelligence is that we want to teach computers to perform tasks without actually programming the computers. That's like the big goal of artificial intelligence, which is far from attainable. So it's not, people speak about general artificial intelligence, but we're far from there. But still, the area in which we are interested more is the use of the statistical algorithms, which help understand and find these patterns. Now, this area got a big boost in the last 20 years. This is a paper from people at Google in 2012, where they actually developed a network like the one that was shown in the talk during the morning, a fully connected network with many layers, and they trained it, and they found that they could generate high-level features using this unsupervised learning. I'll get into what unsupervised learning is in a minute. Basically, they answered the most important questions on the internet era, which is how many cats are there on the internet? And they literally analyzed videos from YouTube in order to see if the network was able to recognize cats on those videos. And they had a good agreement on that. And interestingly, since 2012, the stock price of Google has gone quite up, which has nothing to do. But here's the main question that we want to answer schematically with machine learning. Given data, which can be or cannot be labeled, can we teach a computer to identify the features that are shown in that image? Here's a very cute example. If the computer can identify a dog from a cat, so we can label the image that has a dog and with a 0 and the cat with a 1. So we want to generate a system that learns the statistical information that is encoded on these images and is able to recognize cats and dogs from different images. And that's a general process of learning that machine learning tackles. Of course, for us it's simple because we have ingrained in our evolutionary brains the image of a cat since we are little. So for us, for persons, it's very, very easy to identify a cat from a dog. But for a computer, it's not obvious that it's easy to identify a cat and a dog. But as the people from machine learning have shown, it is possible to train algorithms that do that. So what is the main idea of generating artificial intelligence in this era is that we have a lot of data and we want to extract automatically, if possible, certain information that is helpful, that is useful for the time we live in. For example, we can do tasks as image augmentation. If we have a very low resolution image, we can have a statistical algorithm that learns the features in the vicinity of the pixels and can enhance the image quite quickly. We want to train algorithms that are able to identify objects on images, and they can ideally do it on real time. This is relevant for the industry of autonomous vehicles, which is a booming industry. People are interested in segmenting customers in order to provide better consumer experiences. We want to maybe diagnose patients based on some data relating to their glucose levels or medical records and demographic records and see if they're prone to have one or another type of disease. So these are all examples of the set of tasks that artificial intelligence uses in around the world. Of course, the methods and the ideas of artificial intelligence can and have also been used in certain problems of physics which are of interest for us. A particularly interesting problem is, it's not shown here, I'm sorry, but there are some references that you can check how people is using these strategies to study and how to map the ideas to physical processes. For example, they have generated different sets of galaxies. Some of them are real, observed from the telescopes, and then they simulate images that look very likely, and they try to identify if the algorithm is able to discriminate between the real and the simulated galaxies. Of course, this is relevant for the astronomy community. This is a nice work in which they trained a system to be able to identify states of the Ising model. So they created a lot of simulations on the low temperature, below the critical temperature, and they labeled them as below the critical temperature. They create a lot of states on the higher temperature, and they labeled them with the other class. So they have two classes, and then they train the system to be able to recognize these classes. So this could be useful. And well, then they show that this trained system can generalize without further retraining or new training. It can generalize to a configuration in which the Ising is, instead of being a square lattice, is a triangle lattice. So it can detect, identify the states on a different configuration as it was trained. So this is what the speaker in the morning was telling us about learning and generalizing to other similar problems or similar tasks. Okay, so what's the main idea of machine learning in general? What we want to do is we want to estimate some relationship between what we call predictors, which can be numbers, can be vectors, can be data in a different format. For example, it can be letters, it can be characters, string characters, it can be audio. Most of these can be readily translated into numbers for a computer. I mean, we have to go through a step of transforming the data from whatever data type it has to a number that the computer can identify. And we want to find a general relation between a response and the predictors. The predictors are also called input variables, and in many scenarios we call them also features. That's just a name we use for the predictors or for the input values of these models. And we assume that the relation can be expressed as some function f, which we don't know, of those predictors, plus a noise, some random noise that is independent of the data there, but it's associated somehow to the error that we can incur on having that data. Of course, the data can be any type of data. Here I'm showing a typical example, which was also mentioned in the morning, a task of identifying digits. We convert an image that represents a digit into a vector of numbers or a matrix of numbers, and then we feed those numbers into a set of functions which approximate this function f that we have over here. So we call the resulting of that exercise an estimation of the function we are looking for. Of course, we cannot exactly have the function that we are looking for. So this is not an exact model. This is just an approximation given by the data that we have at hand. So we can only have an approximation here, and we can hope, and in general it happens, that in this approximation of the estimation that we have, the error term averages to 0. So the main steps that we do is we convert to a data matrix. For example, on the digit number data set, we have around 60,000 images of numbers that are all labeled, identified correctly with the corresponding digit. They end up being 784 length feature vector, which is just the size of this matrix when we flatten it out. And we want to learn or estimate how is the distribution of these vectors or how they are distributed in order to be labeled according to the digits that they have. So quickly, if we do a quick estimation of the error from the exact estimation that we don't know from the one that we have, we can see that there are in general two ways or two errors that get split in this. This corresponds to the variance of the noise or the random noise that we have over there, and in most of the cases we cannot reduce it for completely. I mean, it has to be there. It will always be there, and it's referred to as irreducible noise. And this other part of the error, it's usually reducible And the way we do it is either we have a very good statistical algorithm or a very good statistical method, or one of the other techniques that in modern times is being used, you just get more data and more data and more data and more data. And the more data you get, the more that you can reduce the error or the differences in this and be more confident that your estimation is closer to the real function that you want to find. Now, with that in head, the tasks of machine learning can be divided in three broad categories. One of them is called supervised learning. Supervised learning refers to that set of algorithms in which we have data that is labeled. So I have all my information, my data, or my variables, features, and they are labeled. So I know which class they correspond to. Usually labels can be discrete elements of a discrete set. For example, in the number data set, they are labeled according to the digit they correspond. In the example of the Ising model, they are labeled according to A or B if they are on below the temperature, the critical temperature, or above the critical temperature. Other typical, the other category is unsupervised learning, in which we don't have labels, we just have the data, and we want to find some hopefully useful label representation that helps us either label it or understand how the data is distributed. And there's a third one that's called reinforcement learning, which I won't go into here, but it's the kind of machine learning algorithms that they used to play Go against the Go champion a couple of years ago, in which the systems learn from whatever they are generating, and so they get retrained and they are capable of correcting their errors at some point or correcting their mistakes and relearning again. And this is important, of course, in robotics and those lines. So supervised learning, as I said, it refers to examples in which we generally have trained data that is labeled, and we can further divide it into two types of tasks. One is what we will call classification, in which we want to classify the data according to the labels that they have. And another type, a very common supervised learning, is just simple regression. Of course, regression is done on high dimensions because usually we have data that can be very high dimensionally. In the unsupervised learning case, where we don't have clusters, we don't have labels, one of the main tasks there, it's called clustering, in which you want to find similar groups of data and put them together according to some characteristic that is present in the data. Sometimes that characteristic is not obvious, sometimes it is. Another example of unsupervised learning, it's called dimensional reduction or dimension reduction. They put the anomaly detection as a separated unsupervised learning category, but it's a very close to clustering. And recently, a new line of unsupervised machine learning techniques called generative models have been developed, in which the system tries to generate something from random noise. And so it actually learns the structure that it wants to learn, and it's able to generate it from that. And for example, ChatGPT is an example of this type of systems. And there's another popular tool that you feed it with a query, a string query, and it generates an image. So for example, you can say, give me a cat that is sitting in the middle of an auditorium and it's wearing a tie, and so the system will just put those words together, start from a random image, and try to generate a final image that has the information that you passed it. So this is a process called diffusion process. It's actually based on a random diffusion. So I'm going to just describe a little bit the dimension reduction of unsupervised learning, because we are using it a little bit, and I'll go into there. As you could imagine, dimension reduction is very straightforward. You have a data set that lives in a high dimension, and you want to project it into a lower dimension. That's the main task of dimension reduction. There are many ways to do it. And of course, you would expect for an data set like this, a result that shows exactly as if you were looking at the data from above. If you want to reduce the dimension into to a two-dimensional plane, this is the same data being seen from above, and a dimension reduction method just returns this. Another type of dimensional reduction methods, which explode nonlinearities that could be present in the data, give a different projection of the data. So basically, this example that we're looking here, which is what we would expect, is principal component analysis. And this example here, it's called TSNE, which stands for Time Stochastic Nonlinear Embedding. And it's just a way to separate the data from a higher dimension into a lower dimension, trying to put all the data that is very similar into similar points on the projection, and data that is very unsimilar very far away on the embedding dimension. So a point that I have projected here on this side is very unsimilar to a point that is over here. And a point that it's near in this cluster, it's very similar to it. And there are many methods to do this nonlinear dimensional reduction. It can be used, for example, to visualize data. It's a good way to visualize data, and it turns out to have, for example, here we're visualizing flags, country flags, and the method, it's good in discriminating flags by color. So it groups together flags that have similar colors. Here's an example of the dimensional reduction of the digits data set, which is the written digits that we've been seeing all around. And these methods tend to create good clusters in which we can find digits that are very similar. So it's very likely to have a number 2 here, or digits with number 2, and digits with number 8 over here, because they are dissimilar in the feature space that is created by these reduction methods. Okay, so what about time series? We can use all these tools and statistical ideas for working with time series. And in time series, we have similar questions. We have a set of labeled time series, or we have time series that are not labeled. We don't have any label associated to them. So we can do classification or clustering. And then there's another popular application, which is regression, but in time series, we refer to it as forecasting. But as you all know, forecasting is difficult. So especially when we want to talk about the future, it's hard to know. And this takes me then to describe the data set that we are working with. As you all know, the financial market, it's a dynamical complex systems, and it has been an attractive system to study and test tools that are related to complex studies. This is the US market index S&P 500 for the period of 2006 up to 2023. This index tracks the performance of 500 of the largest companies in the US market. Here I'm showing just bands for reference of the main periods of economic turmoil that are associated to this market. And sorry, I should have put them here, but if we refer to the price of an index or a stock as P, as Raúl mentioned earlier, we usually work with the difference of the logarithm values of the prices in consecutive times. So here I'm showing the log, we call this the log returns. So here are the log returns for the US market with the same regions highlighted and some labels there to see what happened and when it approximately happened. And as you can see in one of the features that Raúl was highlighting is that these return series usually have this clustering component, and they are higher when we have a strong market crash or a strong economic event. Although I'm not going to talk about that in this talk. But this is the main object that we're going to use for the analysis of the data that we have. So we have cleaned the stock data set that we have, because we, as another speaker during the week said, not all the companies, not all the 500 companies are trading completely during the time period. So in this time period that we selected, 2006 to 2023, we found that 316 companies were continuously trading. So we reduced the data set to that. And here's a heat map plot of all the returns that we analyzed. The line over here, so we have the log returns. We labeled them from k equals 1 to n. N is the number of stocks that we're using, 316. And we have approximately this long time series, 4,382 time samples. So these are daily closing prices, and we take the log returns. This line here is just, okay, so I can place this in a matrix, which I'm visualizing over there. And the line I put here just represents the window that I'm going to use for analyzing and to describe the results that I'm going to present. And I'm only going to present the results from one window. Eventually, what we want to do is we want to move this window for a shift, which I call tau. It's selected 20, but we will go eventually to 1. So one day we will just shift the window for one day. But for now, I'm just using, well, I'm actually not showing results for the shifting. I'm just, I am showing results for shifting, but I'm using a 20 day. So this is the main data set that we have. This is the slice that I'm going to use of 252 days. Now I'll represent it just with that submatrix over there. So as you can see, which is important, the size of the resulting matrix, so the number of columns that I have, is lower than the number of rows that I have. And this will induce some noise on the data that I analyze here. Now, here is a visualization of the actual time series on the same period. So here is time, and now I'm showing the values instead of looking at them as a matrix. And here the question that I want to ask, or that I want to try to answer with reference to the machine learning tasks, is if I could identify, maybe you cannot see it clearly on the image, hopefully you can, but if you can see, there's a thick black line here, which is a consequence of the overlap of many lines that look similar. But behind them, there are other time series that look a little bit less gray. They look more transparent, which are different. So what I would like to do is to discriminate between those that look like and those that look different using some, in this case, unsupervised tasks. So this is some kind of problem of clustering the time series. And one way to do it, which we have done and has been done, is using the correlation matrix. Now, having in hand and keeping in mind that this correlation matrix, of course, induces noise because of the size of the data set that I'm using. Here is a correlation matrix for those segments. This object is an essential tool in finance. People actually use it to determine the risk of an investment portfolio. So it's a very important object in financial time series analysis, and it's very relevant to take care of the noise that gets induced because we are using short time series here. And there's a lot of research and a lot of effort on trying to understand the noise that is being encoded in this. I'm not going to go through that direction today. And one suggestion is to use results from random matrix theory. So random matrix theory suggests that the eigenvalues of that matrix could be following a random matrix theory distribution, the Marchenko-Pastur, and it was observed, not for my case because I'm using small time series. Actually, this plot is a different financial system, but the main idea remains. The blue lines here is the distribution of eigenvalues of a matrix, of a correlation matrix that is created using time series data. The red curve is the Marchenko-Pastur distribution, and the argument or the hypothesis is that all the eigenvalues that lie in the support of the Marchenko-Pastur are basically random noise. So you can just filter the matrix by eliminating those eigenvalues, and you keep the eigenvalues that are outside as being the informative eigenvalues, and you create a new correlation matrix, which is now cleaner. You have removed the noise. This process is known as noise dressing. But there is a an issue with this, and the main issue is that it just works well if you have long time series, because then you can do this correctly. If you have if your time series is smaller on size than the number of stocks or time series that you have, then this matrix becomes singular, and you have a lot of zero eigenvalues, and this is not so straightforward to do. So there's a lot of criticism into this tool, although people in finance use it. And it has been suggested that other type of methods are maybe better suited for filtering the noise in the correlation matrix. One of them is called hierarchical clustering, which has been proposed a few years ago, and it's been argued by Stanley and Mantegna in their book that it's better to filter the correlation matrix like this. So another way to do is to create communities using your correlation matrix. And once you create communities, you can cluster the time series, and you have found an answer to your solution. Of course, it depends on the correlation time series, so it's not exactly what we want, because we know that there's noise induced on this. Once we have clustered, we can use some of these statistical tools to compare the clusters that we have, and we can create a distance matrix. And with a distance matrix, we can, for example, project that distance matrix into a lower dimension space and see if that clustering is consistent and tells us something useful about the system. But this method is not also the best, because it has some issues with an arbitrary choice of the number of clusters, the estimation of the correlation matrix, etc. So one idea is to use something that we refer to as features of the time series. And features of the time series refer to getting extra numbers from the time series. So converting my time series using statistical measures from them into a vector. So the statistical measures are related to properties of the time series themselves. So we collect a lot of different statistical measures from the time series, and we call this the feature extraction. And with the feature extraction method, we can identify and we can find differences from the time series that we have. So in the last years, a collection of up to 7,000 features was put together by this group over here, which of course, if you have 7,000 features for 300 series is not the best idea, because you have to analyze big things. So by using brute force, they applied all these features to a large set of time series, and they reduced the features to 22 numbers. So this surprisingly 22 numbers captures a lot of the dynamical behavior of many time series. And it's literally a brute force. They ran it over thousands of time series tasks, and they found that these 22 features consistently give good results on solving the assigned tasks of this time series. And the time series range from anomaly detection, EEG data, financial data, etc. It's a very large data set of time series that they have. And so we ask ourselves, what happens if we apply this to our time series? We convert them to this feature vector. And what I'm going to show you next is just a quick survey of the results that we obtained by applying this catch-22. So we have the matrix of returns like this. This is the segment that I'm looking. I expanded it here. And once we convert it to the 22 features, we have a matrix that looks more or less like this. So each row here is the same stock market, but the columns represent the 22 features that we have extracted on each of the time series there. Quickly, they call this a canonical time series characteristics. They are grouped in these 10 categories, and broadly, they describe different features from the dynamics of the time series. So here we see features that are related to the shape of the distribution. We can see that along windows over the whole time series, they change. Here are features that measure some extreme events that are defined statistically on all the methods. So what I want to show you here is that actually these features are changing along the time series. So they might tell us something about what's going on this time series. These are features that measure statistics related to the linear correlation. There are others that measure nonlinear autocorrelation features. symbolic features in which we want to translate the time series into some symbolic representation, which is useful to measure things also like entropy and information. Self-affine features, which refer to this idea of self-similarity inside the time series, and incremental differences, and other features that are labeled there. But the main observation here is that the features actually are changing as a time series. So if we could leverage that change and information and study it, we might learn something of the financial system as well. So that's what we try to do. So we have, again, the time series converted into the feature space. And one little issue here is that all these, as you saw in the plots, all these features range widely on a very different orders of magnitude. So one trick that it's done in machine learning is that we rescale the data. So what we did here is we rescaled all the features to run from 0 to 1. And so we have them all on the same order of magnitude. And using this rescaled matrix, we created a dimensional reduction projection based on the method I described. And it turns out that we can discriminate in different groups for each of these 22 time series. So here I show the resulting projection in a two-dimensional space. And here I'm showing the time series that got grouped on this on each of these segments. And then, so just as a summary, machine learning provides us methods that complement statistical analysis, and they can become useful tools in physics. Features are fundamental for good inputs and good results in machine learning. Time series data is amenable to use with machine learning algorithms, and there is some good toolbox there that help us explore quickly all these set of statistical features that could be relevant to the work we are. Finally, we applied these features to 316 stock from the US market, and well, we are on the process of analyzing these clustering results that we have. So thank you very much for your attention, and thank you very much for staying this late.
Thank you very much. We thank the speaker. So are there any questions or comments? Yes, Marcus?
You mentioned this nonlinear dimension reduction. May you explain very briefly how it works, why it is nonlinear, and
The reason why it's nonlinear is because that the function that's used to minimize the distances is not just a difference between the Euclidean distance in one and the other. They use, I think in the TSNE, they use a distance that's weighted by an exponential function. So they try to expand the distances nonlinearly and see if by expanding you can notice more the dissimilarities between the different points that you have in your data. I can show you later that it's not very complicated math, and it's very straightforward, but it's more complicated to implement it computationally because of the nature of the data itself. But the idea is that instead of using just a linear function to discriminate between distances, which is just the difference of the distance, Euclidean distance usually on one space and then the other, then you use a nonlinear function of that.
Thank you.
Mm-hmm.
Any other questions or comments? So is really sorry.
I'm curious about your specific work. What is the criteria you use when you choose the way you're going to reduce the noise? Because you mentioned two, which is getting more data, and also the other one, which is a statistical algorithm, that it's really good. Mm-hmm. So how do you choose which one you're going to use, and what are the limitations of each one?
Well, let me say it like this. choosing the statistical algorithm could be a limitation if you don't have a knowledge of the variety of algorithms that there are. So we have to go through all the books and papers that are continuously being published and see which one is good, new. There are a couple good books on statistical learning that review thoroughly the main algorithms, statistical methods, which gives you a very broad idea of what can be done. So that's one. Regarding data, well, if you can collect more data, that's good. But one of the problems is that we can't collect more data many times. I mean, big companies can do it, and they are doing it all the time. They're doing it right now in our cell phones and all that stuff. But real people can't do a lot of data collection, and you can't repeat an experiment easily and get more data. So in that sense, if you can't get more data, that's a limitation. So you would try to use a better statistical algorithm or
then for you specifically, you chose the first one, the statistical algorithm?
Yes and no. We are limited by the data that we have from the stock market. But one way to expand the data is to use windows or smaller size and just run them on smaller and smaller shifts. And so we have a very large data. But we can also do it into some point, right? We cannot have very small time series in which I mean, it doesn't make too much sense to have a time series that it's 20 points long and then convert it into a 22 feature set. So we have to trade between that. Fortunately, there are a lot of stock market data around. We only used so far the SP 500. We're planning on using it on the Mexican market as well. We are looking at different financial instruments that you can get data from. So in that sense, we're not very limited from the data because we can use it. And if the financial data aligns to all these stylized facts that were mentioned in the previous set, then it's a good representative data set.
Okay, the last thing I'm curious about. Yes. You mentioned that computationally, it was sometimes harder. So for these two methods, it's almost the same thing, or it's also harder for the other one?
This nonlinear method is computationally hard to implement, like to write down the algorithm. It's not very expensive computationally. The computationally is very quick. There's another method that it's also based on nonlinear mappings, which is more hard computationally. It requires a little bit more of computational power, but it's not, I mean, you're not limited by that. With today's computers, it's really easy. But that takes me to another point regarding to your previous question. We are also limited by computer power.
Yeah.
I mean, if you want to train really big data, for example, cats and dogs and many, many images of cats and dogs, you are limited by computer power. So you need specialized hardware and specialized implementations, which it could also limit. In this case, we don't need very hard computer power for it.
Okay, good to know. Thank you.
Further questions? Okay. So we thank the speaker again and go to eat.
Okay, well, it seems that my risk of value is, so I don't know, it finished full time, so I have to, I had a bet yesterday, I must, that if Germany lost to Spain, I was gonna dance. So, because I come from Veracruz, and I like Spain. If anybody wants to join me, you're welcome. Okay, that's it. Congratulations to Spain. And I'm sorry for getting you.
Okay, welcome to the afternoon session. Now we plan to have a roundtable discussion about, well, you see, physicists' contribution to complex systems, promises and achievements. We are still missing the fourth organizer. Where is he? Okay. Well, I think we met the whole week, and it was very exciting for us to have you all here. And but did we present ourselves on Monday?
I think so, Monday. Yeah, I did.
Okay, so but let's present ourselves again. This is Pablo Lopez from CUCEI. Well, his campus is like 50 kilometers from here. And Denis Boyer from the Instituto de Física de la UNAM. Soham Biswas from here, from the physics department in CUCEI. And myself, Thomas Gorin, also from the physics department. And well, let's start. I hope that there will be a lot of feedback from your side and participation. But I will pass the microphone to Soham.
Hi, welcome everyone. So it was indeed an exciting week for us. So the precise idea for this roundtable is that physicists' contribution to complex systems. So all of us will make some comment, starting from you. And so the idea is that how do you see the complex system? And then we more or less discussed at the beginning when we started working for organizing this conference that what could be the roundtable. And then we more or less discussed in the line that, let's say 30 to 40 years before, a lot of interdisciplinary sciences physicists started working on, like econophysics, sociophysics, biophysics. And there was, 40 years back, there was a lot of promise that about the physicists' contribution. And many new field of science came out, like quantum biology, quantum thermodynamics. Okay, and there are some areas of science which also came out, which appeared to be strange to many people, like quantum finance. Okay, so the idea is that how you see the different areas of these interdisciplinary sciences from the physicist point of view, and how much you think that physicists have been contributing, and the scope of physicists to contribute in these interdisciplinary sciences, which in total we see as complex systems. Okay, so what's your opinion? No, I will just comment. So maybe I will forward to Danny.
Oh,
okay. No, I give the opinion.
Yeah, okay. So, well, I think that we are doing, many of us, interdisciplinary science in some way, or we are interested in things outside of physics. Actually, I'm thinking about the Nobel lecture of Parisi. Actually, there is a recent interview, I think, which appeared in Journal of Complexity. So, which is nice about studying complexities, that you can do something else, something different from physics, something else than physics, and learn about some other disciplines. And I think that's quite a good point, a good starting point. I mean, first, the interest of us for playing with our tools in some other directions and areas. So I think one of the first contributions is to have fun first, and maybe to make some small advances. I think, well, particularly that the specificity that physicists have is maybe to propose, as we have seen all over the week, models, mechanistic models, trying to understand not just, for instance, analysis, or not just empirical experiments, but modeling. I would say that modeling is one of the central part. So, I mean, that's my first brief opinion.
Then we can start from Pablo, your comment.
Want to comment something?
Well, not particularly regarding sociophysics or quantum physics, but I would like to point out also in the fundamental laws of physics, for example, in quantum mechanics or quantum thermodynamics, I think this has been happening some decades ago, and started thinking about for example, openness in quantum systems and complexity all around. This might be also one fundamental part of nature that one just cannot put apart and always have to consider as a whole, for example, right? And so perhaps coming up with new ideas how to approach this kind of problems, but putting aside the fundamental things we have learned since high school, for example, and then start to thinking everything as a whole interacting, which cannot be avoided, and considering this as a fundamental part of the emergent things that can happen and everything that's going on around us. It's also one of the things that I would like to say regarding this.
Yeah. Thanks. Maybe now we can start with all of you. So Hernández is not here, right? Okay. So for maybe Sid. Yeah, Sid. Let's start from Sid.
Why did you put me on the spot? Because I guess I'm the oldest one here now. Well, I guess a couple of comments I have is that in complex systems, it seems to me that one should be very careful to distinguish complicated systems from complex systems. Complex systems, to my mind, are systems with many interacting degrees of freedom in which there is simple emergence coming out from the cacophony of all kinds of complicated interactions. So my prototypical example is this flock of starlings, which they're not very smart birds. They only are trying to avoid their neighbors, and the patterns that they make are so incredibly beautiful. And somehow it doesn't seem that different from what happens in the Navier-Stokes equation, where you start with like a simple, quote unquote, differential equation, unfortunately a little bit nonlinear, and out comes like von Karman vortex streets, turbulence, all kinds of phenomena that in a steadily driven system that you can get incredibly rich time-dependent behavior. So I think in this instance, it's important to like distinguish the complicated from the complex and to ask the right question. I mean, the right question is always key. So that's maybe something to say for the students, which is asking a good question is worth 1,000 useless solutions.
No, could you ask to put the camera to the audience?
I guess it is.
It is? Okay.
Want to say something?
No, I just don't.
Well, I think, I had somehow the idea that, physicist contribution, this is somehow contribution to whom? To society, probably. And does the society got aware of this contribution? Is it society gotten the idea that it's relevant or it's irrelevant what we physicists produce as new kinds of knowledge, maybe? And the first time I saw, say, a theorist of complex systems appearing in the broad media was in this movie Jurassic Park. The crazy guy who was explaining the butterfly effect, right? Don't know who remembers it. So maybe this was the idea normal people have, or the image normal people have about physicists. And I don't know if it is a good starting point, but is this still the idea people have, or did it change? Well, let's think about weather, right? This is certainly a complex system, and of course, there has a lot of work been done by not only by physicists but also by physicists to understand it better. Is it was it successful? Did we fulfill the promises? Or?
May I answer again? Because I detect a smidgen of pessimism in the way you phrase that statement. And I guess I would be more on the optimistic side, because I guess 2 years ago I was teaching at the Perimeter Institute in Canada, and they have a very beautiful building, everything's very lavish, and they have very inspiring quotes on the walls. And one of them is, "The theoretical physics of today is the technology of tomorrow." So I'm not worried about I feel that what I'm doing is quote unquote useless, theoretical physics, toy models. I don't worry about that at all, because, sometimes something that you can never imagine someone seizing on an idea and doing something. I think the best example of that is like GPS or MRI machines, which started from nuclear magnetic resonance. And the guys who were studying it just had no idea that they were of any application. They would just understand, the relaxation of the nucleus under a strong magnetic field. So I think we should celebrate doing useless knowledge. And one other thing along those lines is that the director of the IAS, Institute of Advanced Study in Princeton, a guy named Abraham Flexner, he was the director in the late 40s, and he wrote this incredibly beautiful essay, and it's called "On the Usefulness of Useless Knowledge." It's worth reading.
Thank you, Sid, for this comment. So one of the comment I really like from him is that one should not mix it up with the complex systems with the complicated system. For example, one of the debate from my PhD days I hear about for econophysics, for example, because I'm coming from Kolkata, so there are a lot of econophysicists. And one of the debate people usually make that whatever you are contributing to the econophysics, if it is not useful to the economist in that sense, then what's the point of doing that? So the same argument goes for sociophysicists, same as sociophysics, same argument go for biology, biophysics. So the question one should ask that whatever the physicists are contributing in this field of econophysics, sociophysics, biophysics, or any of these interdisciplinary areas, so how do we really what should we care more? Or do we really feel useless if my contribution to biophysics is not taken seriously by the biologist because they are asking completely different questions than what I am asking? Or I will take it like a social system or economic system or a biological system, a very good candidate to study some physical properties I am interested, what my traditional physics system didn't make me think before that. So maybe somebody else. So then maybe I will ask Jack to make comments.
So I think it's always important to think in terms of the problem. What is the problem? Not the method. The method be relevant. And when physicists start working on problems outside of their field, there's a risk we focus too much on the method and not on the real problems of the field, the real interest, and that we do not know enough about. When I want to make a model of the brain, it is maybe good to know a little bit more about the brain than making some spin glass models, which probably have nothing to do with the brain, only. So there are many examples. So also in physics, it is important to work on the real problems and think about the real questions of the field. And as physicists can contribute. We know that James Simons, for example, had only physicists and mathematicians working for him, and he made $25 billion. So you using basically physics methods. And they solved real problems. And in that problem, it was predicting the stock market in such a way that you can extract money. And for most of the work in finance, I haven't seen that that it's actually very hard to do that. So I think it is important to always keep your eye on the main problem you want to solve, that you have that in the back of your mind.
Hey. Well, I think something important. I think, of course, we do care about results. We do care about if the things that we are making theoretically or the things that we are getting from empirical data, we can get predictions. It's something that is of our interest. But also, we are interested to have knowledge and knowledge that is adequate. And in a lot of systems, what we can know is that we cannot predict. And also it's important to have measurements or to have results about the uncertainty of the systems. And it's something that in general, the population do not take into account that is part of the things. I remember, for example, this football World Cup. Everybody says, okay, Argentina has won or France, but maybe also Belgium that it couldn't pass to the next phase. Maybe also could win because there are systems, there are complex systems with results that are with uncertainty, and it's something important to measure. And my next comment is about that we are now in a different stage in the humanity. I don't know how to say that we have a lot of measurements that we hadn't before, and also we have cheap computers or relatively cheap computers to deal with, and new technologies to use it and to collaborate. So, of course, I think that most of the new contributions of complex systems inside the academia in physics are due to that, and that to have access to data, to new data and to information. And I think that this is something that also we have to go in that direction and to take advantage of that. Many of the different disciplines, like, I don't know, urbanism, sociology, etc., they have been in the past disciplines that try to deal with complex stuff, but that they cannot use measurements, but all ideas or very general criteria. But okay, that's the only point, that the access to new data with measurements, with real measurements, has to effort or has to push new insights of different topics. And the insights could be predictions at most, but maybe not. Maybe it could be only characterizations, but correct characterization of the uncertainty of the systems.
Maybe Francois want to make some comments?
Okay. Well, I have heard, for example, a large number of talks on earthquakes in which, for instance, someone gives his favorite model, then makes a wonderful simulation and gets perfect agreement. On the other hand, I have once had from some wise individual whose identity I forget, told me that if a model only applies to earthquakes, then it's useless or wrong. Well, rather worse, useless than wrong. And that's because the data in earthquakes are so poorly characterized that there is simply nothing specific that you will learn from the fit of a model to the given data. And now I wonder to what extent all of complexity is earthquakes. And so we should be careful. Physics has been historically successful because it studies rather well-defined problems with powerful mathematical tools in the presence of accurate data. Now, I understand that this is somewhat boring, and so we as physicists have gone on a joyride in subjects where this is maximally not the case. I think we should be careful, but certainly it's fun.
But for example, what are the cases of? Just can you give us more examples or some examples of both that we have a specification data with a lot of specification or not exactly?
Just take a table of contents of complex systems, language, the brain, what is it? Finance. I mean, in all of those cases, you have large amounts of data, a very unclear sets of mechanisms, and countless lovely models that will fit almost any data. I think I remember a joke which you have this theorist and this experimentalist. So the experimentalist gives a curve that is like that and draws it on paper. And the theory says, oh, perfect fit, and gives you the theory. The experimentalist says, oh, sorry, the paper was upside down. Oh, no problem. Again, a perfect fit. So I think we should be careful.
Okay, maybe I want to explain a bit my pessimistic view. It's not really pessimistic, but you know, as a faculty at the university, as a faculty member, I feel increasing pressure about the necessity to justify my work, right? Because after all, we are paid by public funds, and they want to know why should we spend money on you, and why are there so many physicists, and so this is why I think it's also important. And then physicists tend to invade other areas, and how well are we really prepared to detect the right problem in, say, economy or in social sciences or biology? And another point I want to make is that our students now, they mostly go to IT companies if they don't stay in academy, and in discussions with other professors and the department, there are then ideas arising that we should teach them more programming and more IT knowledge, because that is where they will work. But this is no longer physics really. So how to deal with that? So this is my doubt.
Following Thomas's comment, I just want to make a comment because I'm a rather young faculty here. So at this moment, what I mostly look for is the new students to get and to make my work done as much as I can to clear the rack of my mind, the ideas. And now one of the thing I usually face that whenever you meet a student and you tell him something fancy, which is not related to whatever the physics you are doing, you tell him, okay, yeah, we will solve these socio-physics issues of blah, blah. And then they're extremely interested. And then when they started learning critical dynamics and then go a little bit of renormalization group theory, they start losing the interest. And then the more fancy word you say and more exaggerate you do, more young people you attract. And then if you start with a very classic problem that this problem is very classic from its own merit, then I found the young people, they start losing interest immediately. So yeah, I really also don't know how to deal with that. So if any comments, that will be nice.
Not so far.
So I want to push back a little bit on your, this pessimism, optimism dichotomy that we're having here. I agree that yes, like as funding agencies, they start saying, what are the broader impacts of your research? And then there's all this metricization of your career, your H index, how many citations, which to first approximation in my mind is all bullshit. And I'm in a very fortunate position because I'm old enough now that I don't need a position. I don't need a place to work. I mean, I've been in the academic world now for 46 years. So, I don't need the position. I can say what I want and do what I want. And I'm very grateful for that opportunity. But I do think that, yes, we are being pushed to show practical applications for our research. And I think we should be always pushing back equally hard that even things that seem useless now could be very important 50 years from now. So I think that we have to keep that in mind and really make the case that it's not citations, it's not how many phys rev letters you have or how many Nature physics papers you have. It's like something that's tangible, a result that means something, even if it's so-called useless knowledge is more important than someone who's, got jillions of citations on some applications paper that has 25 co-authors. So again, I realize that I'm coming from a very privileged point, so I can say this very easily and that I have very little skin left in the game. But for the young people especially, I just highly advocate, try and keep in mind the true values of why you got into science rather than just fulfilling some box in some grand application of what are the broader impacts of your research.
Okay. In fact, I think the important aspect of studying physics is you learn to solve problems. If you change the point of view that we are facing in our studies, we are going to do something different. About the administration and bureaucracy, the bureaucracy not only asks you a lot of requirements in order to give you some funds for research by a project or whatever. Now the universities, the authorities of the universities are following carefully what we are doing, how many students we graduate, the classes we teach, and we must report many things, not to the CONACYT or funds or funding agencies, now to the university. In fact, this is one thing I don't understand, because we are academics in physics and mathematics are the more productive in my university, for example. And we are under auditory all the time. Other thing is we're talking about the complex systems, problems and achievements. I think in that respect, I am very, optimistic, because society is more complex and there are new sciences as artificial intelligence, where physics can produce and research and find new results. In fact, economics call this aspect that you mentioned of invading other fields, like the Tarzan complex of the physics, because suppose we can do everything. This is a complex Tarzan complex. Complejo, how to say it? Okay, in the sense of mental illness or whatever. And other aspect that is important not to forget is that, okay, physics, I don't want to say traditional physics, like high energy physics or quantum field theory is not, there are no new fantastic results in the last 20 or 40 years. And some people, some important physicists say that it's under crisis. The physics is in crisis. In these fields, it is not. And I guess at some point we are going to find new results and new, to be able to find new theories and that, how to say, help to this state of physics in stationary state in the traditional areas, or I don't want to say, I don't want to say traditional, but in order to push them. And I think I am optimistic also, and I think we are to superate this state. Okay.
Thanks. Sorry, because I already warned you that I tend to ramble a lot. A couple of things is that, as Professor Sid mentioned, I think that we all are in a kind of privileged position because not everybody can afford to study physics or study a PhD or do something like this. You need to have some kind of minimum needs cover in order to do that. So from that point, we have already we already are in a better position than most. On that matter, that it's also true that academia is probably due to a transformation, because we are still working with institutions that are, well, time tested, but also sometimes not entirely understood and up to date, especially considering that now you have a lot of people with a PhD looking for a position, and competition is going to be harder. And the way for you to decide which person gets a position is going to be with the promise of how important or relevant their work is going to be. And that's not something that you can judge a priori, I suppose. So that is not a thing that's just peculiar to physics. I think that is unfortunately something that is going to be happening everywhere in academia. And the good thing and a bad thing, I suppose, that in terms, for the case of complexity, is that there are fundamental questions that still need to be addressed. And I will argue that probably complex systems and complexity is kind of the holy grail of the next century, because there are things like emergence and other things that are really peculiar that the people want to understand a lot, or that will have a huge impact if they are better understood. On the same vein, there is also kind of potential limitations, because, for example, just by thinking naively in Gödel's theorem, the fact that there are kind of truths in a system doesn't mean that you can prove those truths. So we have to also grapple with these two competing ideas, that there are like really important things that could be really almost out of reach. But anyhow, that is also kind of an interplay that happens in many other fields. Just to make a comment about high energy physics or other things, I remember a talk of a professor who said, you know, I have heard this joke for 30 years and every year I find it less funny, which was fusion energy is the technology of the future, and it always will be the technology of the future. So I suppose that is something that we can be pessimistic about, in the sense that we can never have a good grasp of when the next breakthrough is going to come, but that doesn't mean that it's not worth pursuing it. Also, well, unfortunately, we also have to figure out that one thing is for the field as a whole, and the other thing will be as your personal life. How much will you try to keep working towards a goal that may be very hard on you. But well, that's another more singular person-to-person kind of thing. But well, I think I will stop rambling.
Maybe let me try to ask a question. So say complex systems. So what are the promises or what are the achievements? This is not pessimistic. I think there are a lot of achievements, but does somebody want to answer that? Maybe not again the same people. Horacio, you want to? Antonio? Who is doing complex systems? Marcus?
Maybe one achievement in this context is that for many systems, at least we understand why we do not understand.
Okay.
I don't know. I mean, in the achievements, I mean, there are some problems that we study a lot now that we didn't study 20 years ago, 40 years ago. So that can be seen as an achievement that the field is ever finding new problems. For instance, nobody cared about networks 25 years ago. And now it's a big framework which is pushed forward for the description of complex systems, right? Many elements that interact in very heterogeneous way. Or I think nobody cared that much 30 years ago about active matter, for instance, or matter out of equilibrium. I think the VSEC model is of year 1995, right? So it's just practically 30 years old. And I remember I was in Mexico for maybe 1 year or two, and there was some talk. I was listening some talk about the VSEC model, which was an interesting model of flocking. Which was receiving a great attention, and it had maybe 35 citations in a span of 7 or 8 years. And now that's a paper which is completely classic paper with thousands of citations. And so, I mean, this is nice that finally some fields are coming. Becoming very important. We don't know exactly why or if they will be useful or useful for what, or if they need to be useful. But the optimistic point of view is that there will be maybe other important problems and frameworks that will appear endlessly, basically. So that would be the most optimistic view.
So then another thing is that, for example, somebody is working on the purely, not in the complex system, but for example, something in stochastic processes or something like that, who didn't work in that interdisciplinary or didn't write any paper in the interdisciplinary area in that sense. So from that person's point of view, how do you think that he will see? Any comments? So, say for example, if you see a mathematician who is working on number theory, right, and now how he will, and now physicists are working on the biophysics, for example, how you think that a person who is not working in the field of interdisciplinary sciences will see the dynamics going on in the interdisciplinary sciences contribution to the physicist from that point of view. One example, for example, I do not know exactly the Fibonacci series, when it had been discovered, at that time, the people do not talk about the petals of flowers, right? But one of the main example we give to introduce Fibonacci series is the petals of flowers, because it's 1, 3, 5. That's how you see the petals of flowers. So what do you think that those researchers who are not working in the field of interdisciplinary sciences will see the dynamics going on here?
So I'll try and answer it partly, which is like, if I think about the number theorists, I mean, they've been working on problems that are 300 years old. And, if you think like the twin prime problem, which there's been incredible advances just in the past couple of years by that Chinese guy from New Hampshire who showed that there's an infinite number of twin primes whose distance was less than some bound. And it's like, it's amazing. So there's fields like that where there are problems for the ages, for the centuries. I think in our type of field, the time scale is like once every decade, roughly speaking, there is some cataclysm, positive cataclysm that happens. There's dynamical systems theory, there's self-organized criticality, there's complex networks, there's active matter. So there's these huge paradigm shifts where all of a sudden, all of your friends are becoming a theorist in problem X, which lasts 10 years before the next one comes along. But I think that if you're trying to look at it from a historical perspective, I think our time scale for really new developments is 10 years, whereas the new developments in, say, pure mathematics, which I think is like number theory, to my mind, is like one of the most beautiful fields of all of science. And I happen to like the twin prime problem. If I had another lifetime, I'd work on it. But, then you need patience. You need 300 years.
Yeah, my comment is related to that. I think if there's real progress in a field, people outside of the field will notice it. And that is what I would, real important discoveries are not discoveries which are only known to people in your field. They are actually not that important if it is known outside of your field. Like random matrix theory is known in many fields. And number theory would know what it is, would know what random matrix theory is. And so I think that is so real important discoveries are beyond their own field. We all know what a Higgs boson is, although the details we do not know, and because it is really important. So I think that's an important way of deciding whether or not actually the progress was significant.
So tagging on to Sid, I would say indeed, we have very frequently papers like self-organized criticality, like percolation, like critical phenomena, flocking, which arise and then eventually peak and go back. I mean, eventually it all disappears. Nobody writes about static critical phenomena anymore. And the question is, how much is the integrated contribution? And I would tend to be a bit skeptical about most of it. Yes, maybe renormalization group is one of the things that is there to remain. The birds, okay, well, they gave us Witchek's paper and Parisian Nobel Prize, but so far, I don't think it's going to be the next FFT. FFT is one of the things that did indeed change human life in a major manner. So it's a bit strange. And to my mind, all the things we love to hear about, like emergent phenomena in the brain, in financial systems, etc., look to be things that may not bring as much as we are led to expect. Sorry about that.
Francois, the FFT is that fast Fourier transform?
Yes. Okay. It's the one thing that made the increase to world national product by 5%, I think. So any other comment in this line? Maybe Sanjeev?
The pessimism is winning. The pessimism.
Well, now that the pessimism is winning again, now, just let me ask a question. It's about many of these, many of the contributions in complex systems has to do with interdisciplinary fields, ecosystems, health, what else, weather, etc. I know the many of the people that the professors here have worked with different groups and in interdisciplinary topics. And my question, if for all of you or whoever wants to answer, is what are the main difficulties that you have faced when you work with other group? For example, Marcus with the psychology and brain measurements, with the weather, with ecosystems in animals, or I don't know. It's what are the difficulties to have this encounter of different disciplines, and also what are the good like the not only the bad part, but also what are the benefits to go in collaboration, not to try to go alone in a different fields.
So that's a good question. It is actually very hard to collaborate with people from another field. I have experience with organizing workshops for both mathematicians and theoretical physicists. And it's extremely hard to make them talk to each other and to even understand what they are doing, because they use a different language. And it takes an enormous amount of patience to have a real collaboration between the two disciplines. At Stony Brook, we have a famous example of that, and that is Frank Yang, Xian Yang, and Jim Simons. They worked more or less on the same topics. Yang was Yang-Mills theory, and Jim Simons worked on fiber bundles. And they didn't realize that this actually was the same, but the offices were close by, and at some point they started talking, and that took a couple of years before they understood that they actually were working on the same problem. So it's actually extremely hard to actually absorb another field. So I think ideally, if you work as a physicist on a different field, you should work 5 years on problems in that field in order to really understand the problems and the questions of the field. It is not easy, even for close by fields, to actually absorb the main questions and the knowledge. But it can be done, and people can make great progress, as was the case with Jim Simons and Xian Yang, because that language is now used all over the place in theoretical physics.
So for people who know me well, I mean, it's very strange to take the role of an optimist, but I want to take the optimistic perspective, which is, I agree with Jack that, yes, sometimes it's really hard to learn the terminology of another field and to try and ask a question that two people from two different fields say, this is an interesting question to my field and to your field. But I've had a couple of collaborations where that's happened, and oh my God, it is so refreshing. You learn a new field all of a sudden, you come into an office, you don't know anything about some field, and you talk to someone and you learn all this new stuff, new phenomenology, new language. And when you can make a contribution in another field, it is like a real high. So I highly recommend it if you can ever get involved in it. I mean, it's sometimes, I mean, with the right collaborator, it's really worth the effort.
I just want to make a comment following the Seed's comment. So yeah, the right collaborator is a very important point. So the first time I hear about this language dynamics and so on, that was at the end of my master's degree, beginning of my PhD in 2006, when there was a paper came out for studying the Indus Valley script. And before that, there was a bit of a debate that Indus Valley script, how much language it is. And then they wrote a paper in Science saying that Indus Valley script is actually a language, and there was 5 authors. I still remember one of them are physicists, one of them are mathematician, one of them are computer scientist, one of them are historian, and another one of them was anthropologist. So, and then in that colloquium, the physicist who was giving the talk in the first half an hour, he just explained who contributed what. And then if you look at that literature, then you will see, we saw at that time, this debate was going on for some long time, and that there are independent papers in the field of historians, anthropologists, computer scientists. I do not know how much physicists and mathematicians have been there. But when these 5 people got together and they wrote this paper, it was amazing. So yes, it's hard, and finding out the right collaborator is maybe the key point. Any comment?
Yeah. Also, I mean, what happens also is that people from other disciplines seek us, look for us, because they need, in a way, some help to do something that is more natural for us, despite of our ignorance to do. And as you mentioned very rightly, I mean, the problem that sometimes the problem that we think interesting are not interesting to them, and and vice versa. So yes, this is complicated, but actually when it works, which is rare, probably, yeah, this is rewarding in a way.
Switch to questions from the audience. Okay, maybe, I don't know, just let me ask in general, are there questions from the audience, the students in particular, or comments? Maybe even, what do you think about your future in physics? Or will it be in physics or not?
Sorry, before you asked to the students if they want to be physics or not, something come to my mind, and is the problem with the ideology in some areas of knowledge. For example, some social sciences and general studies, and that they are anti-scientists. And in fact, I think some conservative anti-scientist forces are trying to take power in academia, and then in some universities they have been successful. And this is another thing we must face, because, for example, CONACYT was taken by these kind of forces, like black forces or whatever, dark forces. And it was a very bad period. I don't know what's going on in the future, but this thing of obscurantism happens, and we must face this kind of problems also.
Maybe one comment to what you said, that other fields are maybe seeking for us because of they hope that we are solving problems. I don't think that is very true. I mean, at least from my experience, I mean, I'm working together with neurophysiologists or psychologists, and for these people, I'm a person who is trying to solve at least some maybe unnecessary technical problems, but is not doing real science. I mean, I'm not doing really brain science or whatever. I have a very concrete example where an ex-PhD student did here in Guadalajara and this Neuroscience Institute, some postdoc, And they were, at the very beginning, they were very happy and they thought, well, now we will analyze a huge amount of data because this physicist is coming. And the opposite was true, because she was questioning anything over there and the techniques, how to analyze, and so, etc. And I think in many cases, we present some quite uncomfortable disturbance. However, this uncomfortable disturbance might be quite productive in a certain sense. And here I agree with you. If you find people which are sufficiently patient, it's really refreshing. I mean, that is really nice, because it gives, at least to me, the chance to learn perspectives on brain dynamics, which I couldn't achieve alone, and it's really very beautiful. And hopefully these people may also take some advantage from me. But in general terms, I'm quite skeptical.
Yeah, what I meant actually that maybe 99% of the people of another discipline do not care about physicists. I completely agree. But it's about the other 1%, and that can be where things that are different can happen a little bit. But I agree.
I was just going to make a suggestion. Why don't we pass the microphone to the back row of this room and just have the young people just say anything they want to say?
Excellent idea.
Okay, maybe I can make a comment about what Thomas said at the beginning on whether the society thinks that they need physicists or not, related to our future, right? Because you ask, how do we see our future? And I think that I talk in the name of my classmates when I say that our future is complex, right? Because, you know, not everybody has such a good position as you. And, you know, I think that in many times, we don't want to work in the IT companies, but we are forced to work to the IT companies. Because I think that especially in Mexico, where these cherry forces take CONACYT and the government, we don't see too many opportunities for us. So maybe the others can comment on this.
Come on, possible.
Well, I want to thank you, professors, because, well, for the meeting. To be a PhD student, for example, in my case, is like being a closed bubble, no? Because now I figure out what the fields and the studies that you do when you are studying. For example, in my case, you are so into your work and forget about to meeting people and start hearing other ideas and all that kind of stuff, no? So I appreciate that you give us the opportunity to hear this word, to trying to know people that do the same things that we do. And I don't know, from this perspective of being a student and the future, I guess it depends on all of us, not to figure out what, as a person, we want to do in the future, but as a whole, as an academy, as a university, to trying to figure out not only for the professors, for the students and for the ones who will come in the future, no? In these fields. I don't know what more to say.
Okay, thank you. Thank you.
Okay, we are hearing some comments from the PhD students mostly, but I can see here are at least 4 licenciatura students present. So you are just starting, okay, to see how the research world look like. So if you have any questions or something you want to ask, comments. 2 of them have the microphone already.
Oh, what are your family, or what is your family thinking, or what did they think then when you told them that you want to study physics?
Well, I'm in bachelor, so I'm really enthusiastic to study a postgrad master degree and also a postdoc and these things. So in an optimistic point of view, I want to see what the physicists could do with these all specialistic things that we can learn about this interaction on big system and these things. So I guess with the things that already say Paulino, in which in this time there is a many data available in which we can make useful things, study this data. So for all the invited speakers and also all the participants, I want to ask if you can do, or if you can contribute to the society with your knowledge, taking apart all these investigation specialists and these things. What do you think that physicists can contribute to the society? It's an open question.
You answered with a question. That's very intelligent.
Me? Well, I think there could be a lot of things done with the data analysis, but I think one of the important parts is that the students should somehow learn how to be innovative from what they want to also develop, not only to do the data analysis, but go forward of that. I mean, go beyond that and try to come up with new novel ideas, perhaps also in how to do the data analysis, or maybe also to move to other type of problems with the techniques already known in this type of fields. And I don't know, that's actually there are many things, I think. I do believe that being physicist and having the right tools, mathematic tools, and that, I mean, one can do a lot of things and can be involved in a lot of things, but also there's always this problem when merging different fields. It takes, as it was said here, a lot of time learning other stuff and a lot of disposition, but if one has the will of going into that direction, that can be done, but just a lot of motivation to go in that, and a passion also. I think it's really important here. Yep.
Well, I won't say what is the social benefit to go into physics or to the postgraduate or studies or PhD in general, that because there are specific topics that they're still there to be solved, and here, I mean, in the academia will be solved. I don't think that will be in other parts, but there are specific topics that they have to be done now. But I won't tell about that. But I will tell about a different part that I'm now involved. That is kind of an indirect social benefit. I think there is a social benefit of this this education or strong education in physics. Now, well, I'm working in the government in a small office, and I think that we are 3 or 4 physicists with PhD or near PhD, and there are specific stuff. For example, in the government, in an office of the gobierno ejecutivo, no sé, del estado, no, I don't know, but in the office we developed technology. That, for example, we developed a model for neural networks to detect retinopathy. There is a disease that is a disease that makes that the people get blind when they are diabetical, and is the first cause of blindness in productive age, and we can it's something that for example in Malaysia, where is it, in this country Malaysia, in 2013 the Minister of Health made a statement that at least 60% of the people with diabetes had to have a check of the eye to check if there is retinopathy in early stages, because it's much easy to prevent. But 60% of the diabetic people is a lot. 1 of 11 persons in the world have diabetes. And here in Jalisco, this should be like for all the people with diabetes has to make a check in the eye to check if there is the retinopathy in early stages, and it's 500,000 people. 500,000 people has to make a check, and there are 50 or 100 specialists in Jalisco that can perform that test. So there is no way to do it, and that's in all the world is the same. Is the same. And what in Malaysia did, what they did is, instead that the physician that can check the eyes do it personally, they took with certain cameras that can take a photo in the bottom of the eye. It's a specific camera. They send electronically the images to the specialist to make the validation. And the point is that in all the world, there has been efforts also in Malaysia to, instead that the specialist can see it and evaluate first, and a tool of artificial intelligence can make this evaluation. And it's not a diagnostic. It's similar to the mastografía. I don't know in English, it's mastography. It's similar, that it's not a diagnostic, but it's something that can have a big scope to get to check a lot of people. So you can people that had in mastography, if you can check people with probability to have cancer or something to check, then only those people you send it to the health institutions, and well, that's a part here. The models that we made here, we have like 7 publications. We got a prize in UNESCO, like one of the between the top 100 projects of IA in the world. We got in the first 10. So it's like kind of a project that could do it because of a person that this Ulises Moya. He was a student from here, from Guadalajara, but he specialized in image recognition, and it's a particular project that possibly can have an impact in society, and it was due to this high formation in technical formation in physics, and it's kind of an example. Another example, simple, is I got extended a lot, but is that, for example, there are few times I have been working 3 years in the government. There have been very, very few times that other people with high rank level in the government ask us for recommendation for something. Or like in COVID, there was a statement of someone, And if we want to answer at like the government and when we are asked for recommendations or to analyze certain things, we do a kind of peer review, in the sense that some of our group work on the points to recommend, and then we gather together and try to see what is wrong, what is right, and try to polish our statements. So all the recommendations can have, before that we send a recommendation, or before we trust in our knowledge, we first try to check if something is wrong of what we think, and to try to polish the things that we can, that maybe we can present at the beginning. And this is important also for doing codes, also that doing coding review, doing peer review, and it's something important in the core of for the discipline of physics that can be applied for different things.
So I have been a graduate program director for 10 years, and I always had to motivate the graduate students what they actually had to learn for the PhD. And the learning goals were 3 things. The first thing was not to believe in anything. And the second thing was not to trust, the second thing was to think for yourself. And the third thing is not to trust any authority. And I think if you learn that with a study in physics, this will benefit society a great deal, if there are enough people who can actually do this.
Are there more questions, comments? Well, this was a great comment by Chuck, I think. I liked it a lot. Unfortunately, well, no, I would again be pessimistic. At least in the early stages of a student tends to trust much more in others' work, say. So we give a problem, for instance, and then the first impulse is to look in books and to see where it is solved, and take the solution from there, right? And not being careful enough whether it's really the answer to the question which was posed. So yeah, this is very important, and it's difficult to learn. That's also true. Okay, again, questions, comments?
Just another quick comment about the importance of physics in our area, our like in discipline, is that we also are pursuing the evidence of the things, in the sense that do not trust or the authorities or the things is all. If people say, "Oh, it works," okay, what is the evidence that it works really? And there is a lot of how to say,
transformations,
vacíos en el holes. Yes, a lot of holes in the industry, in the government, in a lot of parts where the people think that something works, but only by some beliefs, but without having the evidence or the right evidence, or doing the controls when you measure something. And this is also something very important in our discipline that we have to encourage.
Okay, another comment? Oh.
Yeah, I'm a little bit out of place. I'm not a physicist. I'm not even a biologist, but I love quantum biology. So in the lab where I work, we work with a lot of physics, mathematics formulations, but we frankly don't understand them. So I think the work of a physicist is very important because you are like the bridge between the theory and a little bit of the application. So that's for me really important. I would like to be a physicist, but I'm a little bit out of time. That's why I think I came here to learn a little bit. When I try to learn a little bit of the theory, it's a little bit difficult for me, but well, I have to try, right? And here, well, we are studying to implement ideas from quantum to biology and information biological gap that we have found. So that's, I think physics is like the bridge between two different states of the science. That's all I can.
Okay, well, thank you very much. Further comments, questions? Sanju.
No, I also keep hearing a lot, let's say, okay, what is the useful of physicists to the society, or what is the useful of your work to something? See, I mean, it's good to be, I actually completely agree with Sid. It's good to be useful to something, but one should also keep in mind that, I mean, we are independent scientists and the theoretical physicists are not a service department to somebody else. Okay, so I might, in fact, when you go to a different area, like say biology or something, I might look at a problem and I would like to understand the problem the way I want. So I don't care whether my understanding will improve the field of biology or not. The similar way, probably biologists, so whether the question we are asking, whether biologists care that, okay, what I do in biology. So at the same time, probably I also don't care whether my understanding of the system improves the study of biology. There are some cases, of course, I mean, if you keep doing that, slowly both the field will probably come closer and there will be some collaboration. But I think at the end of the day, I think we basically look at it as a complex system and we want to make it simple models, probably the minimalistic model, and we basically try to understand the way we want to understand basically. So, I mean.
Okay. Okay, well, then some comments. Or let's close. Then thank you very much for your attending this discussion and for participating and for your comments, questions. And let's go to the coffee break. And after that, we will have the closing ceremony. And okay.